All right, let's go through this one. So we've got the integral of a product of two functions that don't look anything alike. What do I mean by that? That's a polynomial, right? It's x to the power of something. This is a trigonometric function, right? These two things, unless you use Taylor series and stuff like that, these two things are pretty much unrelated, okay? So if I've got the product of two functions and I want to integrate them, can anybody remember a rule or a technique that we can use to help us out?
Integration by parts.
Good, yeah. Remember, it's the reverse product rule, okay? That's the equivalent in differentiation. That's how we came up with it. So we said the integral of two functions, one of them is called u, one of them is called dv, should be equal to u times v minus the integral of this thing the other way around, so v times the derivative of u. Okay, now remember that is in the formula sheet in case you're having any difficulties remembering, but you remember that when I derived it for you, it was just literally thinking about the product rule. So the derivative of u multiplied by v is equal to the derivative of u multiplied by v plus the derivative of v multiplied by u, and then just thinking about what happens if I integrate both sides and I get this out. Okay? So I need to let one of my functions be equal to u, or one of my functions be equal to the derivative of v. Which one's going to be which?
In this case, x is u.
Good.
And cosine x is dv.
Okay, perfect. So let's write that in. So we're saying let u equal my x, and my derivative of v is equal to cosine of x. Now my next question is why?
Because you can't derive cos or trigonometric function to nothing, whereas x can be cancelled out to a constant value of 1 in this
Perfect.
case. Then simplifies the integral from the right.
Excellent, that's exactly the reason why. So whatever you let your u equal, remember that the next stage, the right hand side is where you're going, right? You're sitting on the left hand side at the moment, you're going onto the right hand side. On the right hand side there is another integral, but the integral is involving the derivative of u. So the idea is that whatever you let u equal, you want to let it equal something that will differentiate eventually to a constant, right? Because then it becomes very easy. Right, the whole thing that makes this hard at the moment is we have a combination of a polynomial and a trigonometric function. So whatever you let u equal, you want to let it equal something that will eventually differentiate down to a constant, because then you're just going to be left with a trigonometric function. Clearly, if you let u equal cosine of x, that's just going to keep going then to negative sine of x, then negative cos of x, then sine of x, then cos of x, then negative sine of x, etc. It's going to keep going round and round and round, right? If you let u equal x, the next stage, which is du, in this case will just be 1, because I've differentiated that with respect to x, right? Hence that becomes a constant, which means I work over here, I'm just going to be left with a trigonometric function, no polynomial. Hey, happy days, right? Okay, fine. Okay, here is derivative of v is cosine of x. I don't want derivative of v, I want just v. So how am I going to find v? Yeah, good. So just remind me, remember my circle, if I differentiate, this is differentiation, sine goes to cosine, goes to differentiate cosine. Good. Differentiate negative sine, negative cos, differentiate negative cos, back to sine again. Okay, so that's derivatives, right? That's derivatives. Clearly, if I'm integrating, which is what I need to do in this stage, I've got the derivative, I want the original function, right? You're happy I'm just going to have to go back the other way. Okay, so at the moment I'm sitting at cos, I need to go back the other way to integrate, that becomes sine. Perfect. Does that make sense? Okay, now I can just apply my formula. Okay, so I'm saying that this, which is really this thing here on the right hand side, should be equal to u times v. U times v, right? So it's going to be equal to x times by the sine of x. Then I'm going to have to subtract the integral of v times du. So the integral of v, which is sine of x, times the derivative of u, that's just 1. Okay? I could write times 1. I'm not going to bother. Okay? That's a lot easier than the thing I started with. Always remember that you want this integral, in other words, the integral on the right-hand side of your equation, you always want this to be an easier thing to calculate than the thing you started with. Okay? Are you happy? The integral of sine of x is a lot easier than that integral that we started with. Okay? If it's more difficult, chances are you probably let u and dv be the wrong thing. So go back and try and swap them over and see if it comes out a little bit easier. Okay, so we have x times by the sine of x minus integral of sine of x. What's that going to be?
Minus cosine.
Yep, at sine, go backwards, comes negative cosine. So negative cosine becomes positive cosine. And of course, don't forget the plus c. That make sense? That'll be your final answer. Okay, are there any questions about that? No? Okay, that's fine. Okay, so there's lots of integration questions there. I have put answers to all these integration questions, by the way. The first one should be all right. Yeah, I think the first one is relatively straightforward. Do you want to go through it?
Me?
It's up to you, anybody.
Oh.
So maybe just look at it for 30 seconds, think about how you tackle it. I mean, we can go through it. We can go through them all sequentially.
I need to study this one.
Okay.
Where are you going? This is the one I have to put.
I think everybody.
I recognize this.
No,
Then you can't answer the question.
no, I could. It's just.
Do you want to go through question 1 then?
Yeah, I kind of.
All right, let's do it.
The second one is review.
Yep.
The first one, can you just split it? The first one then.
Yeah, absolutely. Well, kind of. Depends what you mean by split. What do you mean by split?
The plus sign. I don't know if it helps or not.
Okay, yeah, so first of all, let's let's integrate each of these separately. That's just a power, okay, so which means we can apply the power rule. So raise the power by 1, divide by the new power. So let's do that one first. So I could write that as the integral. Actually, I'll split it into 2, so that's a good idea. So I'll put the 3 out the front. Don't worry about the constants, a bit awkward. That becomes x to the power of a half with respect to x. That's the first bit done, right? The second bit, I'd add the integral of 4 over x minus 5 with respect to x. Okay, let's do this bit first. Let's do this bit. What would the integral of x to the power of a half be?
That'd be 2x3 over 2.
Ye-
Sorry.
Yes. Yeah, that's right, yeah.
Sorry. No, wait, I'm wrong. I'm saying it's 2 divided by 3 to the power.
Okay, yeah.
Times 3, yeah.
Yeah. Times by x to the power of 3 over 2.
Yeah.
That's fine.
Sorry.
That's fine, yeah. So I thought you said 2 because you cancelled the 3 and the 3, but that's fine. So yeah, you'd raise the power by 1. So if you take a half, raise it by 1, so half plus 1, that's 3 over 2, or 1.5. Leave it as 3 over 2. Always leave it as 3 over 2, right? So x to the power of 3 over 2 there. Then you need to divide by that new power. That's literally what we came up with in red on the right-hand side of the screen for question 1, right? So we've raised the power by 1. If we divide by 3 over 2, that's the same as multiplying by 2/3, right? But of course, we've still got this 3 here. Okay, so it'll be 3 times this. Does that make sense?
Can you explain why we write 2 over 3 here?
Yep, absolutely. So are you happy, first of all, if we raise the power by 1, we get 3 over 2? Okay, so if I divide something, let's just say 1 divided by 3 over 2, okay, because that's really the coefficient there, right? So,
Yeah.
so that's exactly the same as 1 times by 2 over 3, which of course is just 2 over 3. That's the reason why there's 2 over 3 there. Okay? Okay, good. Let's do the second one. So the second one is not actually that bad.
Just the squares thing, right?
Not quite.
We do. Okay.
Not quite actually.
Yeah, x minus 5 times x plus 5 divided by x plus 5.
Oh, you could do. You could absolutely do, but I think actually there's a slightly quicker way.
Okay, sorry.
Sorry, don't worry.
Yeah,
It's a good idea. Yeah, it's an absolutely fantastic. Whenever you've got a quotient, okay, so I want you to kind of get into this habit. Whenever you're trying to integrate a quotient, what do I mean by a quotient? Just two things divided by each other, okay? Always, always, always check this. So always check whether you have the derivative of a function divided by the original function or something close to it, okay? Because of course, if you're integrating that, you know instantly that that's going to be the natural log of the function on the denominator, okay? So just remember, we kind of went through this when we're dealing with natural log. So this is natural log. Let me write it a little bit neater, okay? So remember when we differentiated natural log, we used the chain rule and we said, okay, the natural log of a function differentiated should be equal to this, just using the chain rule. So if you're using the idea of derivatives are inverses of integrals, then we can say if we have the integral of two functions being divided by each other such that we have the original function on the denominator and the derivative of that function on the numerator, it should be equal to this, just using the idea of antiderivatives, differentiation, integration, inverses. Let's check that. So always get into that habit. Whenever you see two things divided by each other, always check this, okay? Now, if I say that's my original function, x minus 5, what's the derivative of it?
1.
It's just 1. That's close, right? In the sense there's no x's and no x squareds or anything like that. 4 is pretty close to 1, right? It's a constant.
Yeah.
That's what I'm looking for. So actually I can turn this 4 into a 1 really, really easily. Okay, and I can turn it into a 1 by putting the 4 out the front. And then that just becomes a 1 there.
Oh.
Does that make sense? Because 4 times that is going to be 4 over x minus 5. Right? So always think, what do I need? Well, I need a 1 there, then it'll be nice, right? I can make it a 1 there by putting the 4 out the front. Okay? Sometimes you also need to divide and multiply by things as well to get that fudge factor going. You can do more examples of that if you want. Okay? But at the moment, if I put a 1 there, so I ignore the fact that there's a 4, in fact I'll just write the 4 times down here in preparation, then this is exactly the same as this situation. Okay? So in other words, I'm saying that the integral of 1 over x minus 5 is exactly the same situation as this, because I have the function on the denominator, the derivative of the function on the numerator. Thus, this should be equal to the natural log of the x minus 5, the function on the denominator. Does that make sense?
Yes.
So always get in the habit of checking that. When you have the integral of two functions being divided by each other, always, 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 always check this. Okay? Because if you can get this out, your life is easy. Right? Okay, so just tidying it up ever so slightly. 3 times by 2 over 3 is just 2. Then x to the power of 3 over 2 is the square root of x to the power of 3. Okay? So just using your powers and indices. And then plus, and then I can just leave that 4 natural log of x minus 5. There you go. That'll be your final answer.